sun of high desert intensity, a brilliant and almost surgical light fell upon a world defined by stark clarity and hard, undeniable edges. It was a light that seemed to tolerate no ambiguity, a light that belonged to a landscape of raw geology and fundamental truths. In the summer of the year 1950, this unforgiving light shone down upon the isolated mesa of Los Alamos, New Mexico, a town that was itself a living, breathing paradox. On its surface, it was a carefully constructed fiction of American suburbia, a place of quiet, winding streets, neatly trimmed lawns, and the innocent laughter of children playing in the sprinklers. It was a facade of profound, almost aggressive domesticity. A thin and fragile veneer stretched tautly over a core of unimaginable world-altering power. This was the city that had been secretly built on a remote hill, the isolated high-altitude laboratory where humanity had reached into the very heart of the atom and had pulled out a fire capable of unmaking suns and ending worlds. The minds that walked these quiet suburban streets, the men and women who headed to the heavily guarded technical areas of the laboratory or to the communal commissary for a simple lunch, were minds that had irrevocably bent the arc of human history. They were the architects and the engineers of a new, a terrible, and a brilliant atomic age. They lived and they worked in a pressurized bubble of their own creation, a place both physically and intellectually sealed off from the rest of the world, a community that breathed the thin air of both the 7,000-foot altitude and of secrets so vast and so potent that their release could buckle the very foundations of global civilization. This particular summer, the thin, dry air of Los Alamos was alive with a strange and unfamiliar new static, a current of rumor and unease that had managed to penetrate even its fortified isolation. A peculiar and persistent wave of stories, of whispers, of blurry, ambiguous photographs, and anxious, sincere eyewitness accounts was sweeping across the vast expanse of the nation. Unidentified flying objects, strange aerial phenomena of inexplicable origin and seemingly impossible technical capability were being reported in the skies with an almost epidemic frequency. Flying saucers, silent gleaming discs of polished unknown metal, were said to be performing incredible instantaneous maneuvers that defied every known law of aerodynamics and inertia feats that made the most advanced jet aircraft of the day seem like primitive, clumsy toys. They were described as transient, inexplicable ruptures in the expected and predictable order of the sky, brief, tantalizing and deeply frustrating glimpses of a technology so far beyond the human grasp, so alien in its performance as to be utterly indistinguishable from an act of pure magic. For the brilliant, accomplished men and women of Los Alamos, these strange and persistent stories held a unique and deeply personal resonance. They, more than any other group of people on the planet, knew precisely what it was to command a technology that appeared magical and godlike to the uninitiated. They understood with an intimate and chilling clarity the immense and almost unbridgeable gulf that could exist between one level of scientific understanding and another. The atomic bomb itself, the terrible and brilliant secret they guarded, would have been seen by a person of the 19th century not as a product of physics, but as a miracle, an act of a wrathful and all-powerful God. These strange silent lights in the summer sky presented them with a chilling and deeply unsettling inversion of that very dynamic. For the first time, the celebrated Nobel Prize-winning physicists of Los Alamos were confronted with the stark and humbling possibility of being the primitives in the equation, of being the ones looking up from their muddy fields in uncomprehending awe at a power they could not even begin to fathom. It was in this strange and charged atmosphere, a unique psychological brew of quiet, justifiable pride in their own world-changing accomplishments, and a new, deeply unsettling anxiety about the true vastness of the unknown cosmos that four men walked together to get their lunch. They were physicists of the highest caliber, colleagues at the laboratory and friends. Their names, now etched into the history of science, were Emil Konopinski, a brilliant Polish-American physicist who had worked on the hydrogen bomb; Edward Teller, a volatile and visionary genius, the future father of that same hydrogen bomb; Herbert York, a young and brilliant nuclear physicist who would later become a key scientific advisor to presidents; and their senior colleague, Enrico Fermi. Their conversation as they walked under that brilliant, cloudless and unforgiving New Mexico sun was light, speculative, and tinged with the professional curiosity that was the hallmark of their trade. They casually discussed the recent spate of UFO reports, dissecting the topic with a playful but rigorous skepticism. They made jokes about the flimsy, anecdotal nature of the evidence, about the public's well-known capacity for mass hysteria and its tendency to see patterns in noise. Teller, ever the provocateur and deeply enmeshed in the paranoia of the early Cold War, worried aloud, only half-jokingly, about the terrifying possibility that the sources might be a secret next-generation Soviet weapon, a technology of such incomprehensible sophistication that it rendered all of America's atomic advantages obsolete overnight. They played with the numbers, estimating the immense probabilities against interstellar travel, the vast and almost unimaginable distances between the stars, the colossal energy requirements for such journeys. It was on the surface a pleasant, stimulating, and purely academic diversion, a familiar intellectual exercise to pass the time on the short, sun-drenched walk to a midday meal. They arrived and took their seats in the rustic, cavernous dining hall of the Fuller Lodge, the historic log and stone building that served as the social and communal heart of the isolated Los Alamos community. The vast room was filled with the familiar, comforting lunchtime chatter of hundreds of other scientists, engineers, technicians, and their families. The smell of freshly brewed coffee and simple, hearty cooked food hung in the warm air, a scent of reassuring and profound normality in a place dedicated to the abnormal. The conversation at their table naturally drifted to other, more immediate topics: a particularly difficult calculation in a current project at the laboratory, the latest political news from Washington, the mundane details of their families and their lives. The strange and distracting topic of the flying saucers seemed to have been thoroughly discussed and then casually exhausted, a momentary and amusing curiosity that had faded as quickly as a contrail in the high-altitude sky. But for one of the men at that table, the thought, the central nagging kernel of the problem, had not faded at all. It had taken root in a mind of singular and extraordinary power, a mind that was legendary among his peers for its unique ability to see directly to the physical heart of any problem with an almost preternatural speed and clarity. Enrico Fermi was a quiet, unassuming man, a recent immigrant to the United States, a Nobel laureate who had been the chief theoretical and experimental architect of the first self-sustaining nuclear chain reaction. The single event had made the atomic bomb possible. He possessed a unique and formidable talent for what his admiring colleagues simply called Fermi estimates, or back-of-the-envelope calculations, the uncanny ability to arrive at a reasonably accurate answer to any complex physical problem, from estimating the total explosive yield of the first atomic blast based on the simple flutter of a few pieces of paper, to calculating the approximate number of piano tuners in the city of Chicago using nothing more than a few well-chosen physical principles, a handful of reasonable assumptions, and a remarkable intuitive feel for the fundamental numbers that governed the universe. As the lunchtime conversation ebbed and flowed around him, a lively but unremarkable discussion of terrestrial matters, Fermi's mind was quietly and with an astonishing speed working on a different scale. He was no longer thinking about the flimsy anecdotal evidence of the sources themselves. His thoughts had moved far beyond the blurry photographs and the excited eyewitness accounts. He was now grappling with a much deeper, much broader, and far more fundamental implication that the very idea of alien visitors, however improbable, had unlocked. In the silent, invisible architecture of his thoughts, he was building a simple, powerful, and devastating model. It was a silent, internal calculation that started with a few simple and what he considered to be eminently reasonable and even conservative assumptions. He began with the age of our galaxy, a number known even then to be immense on the order of many billions of years. He considered the sheer overwhelming number of stars in our Milky Way, 100 billion suns, a number that was already known to be a significant underestimate. He factored in the high probability, even a logical necessity, that many, if not most of these stars would be orbited by planets, and that a significant and non-zero fraction of those planets would exist within a stable habitable zone, temperate region, where liquid water, the essential medium for life as we know it, could persist on a planetary surface. He then made the most crucial, the most pivotal, and the most optimistic assumption of all, that the emergence of life, and subsequently the evolution of technological intelligence, was not a singular, divine, or miraculous event unique to this one small, wet, and insignificant world. He assumed, for the sake of the argument, that it was a reasonably common, if not an inevitable outcome, of the universal laws of chemistry and biology playing out over the patient, vast, and fertile timescales of the cosmos. From these simple and seemingly unassailable starting points, a conclusion of staggering, monumental, and unavoidable force began to emerge, to crystallize in the silent, logical machinery of his thoughts. The plates at the table were being cleared away by the commissary staff. The conversation around him had turned to a recent humorous cartoon that had appeared in the New Yorker magazine, a drawing that playfully depicted industrious, saucer-flying aliens stealing public trash cans from the streets of New York City. The mood was light, the meal was effectively over, and it was in that precise moment of post-lunch levity, a moment of perfect, mundane, and reassuring normality, that Enrico Fermi suddenly, and with a startling abruptness, looked up from his deep and silent thoughts and asked a question. It was a simple question, a guileless question, composed of just 3 elementary words. He did not shout it for effect. He did not pose it with any great theatrical or dramatic flourish. He asked it with a tone of genuine, almost childlike, and deeply puzzled curiosity. He looked around the table at his companions, his eyes holding a strange and unforgettable mixture of wry amusement and a deep, penetrating, and unsettling seriousness, and he asked with a quiet and clear voice that cut through the surrounding chatter, "Where is everybody?" The lively conversation at the table instantly stopped. Teller York and Konopinski looked back at him, their faces a mixture of momentary confusion and dawning comprehension. Everybody in the literal sense was there. The dining hall was full of people, but they knew Fermi. They understood his mind the way he thought in scales and in orders of magnitude, and they understood, with a sudden, creeping intellectual chill that instantly cut through the warm, pleasant afternoon, that his question was not about the room, it was not about Los Alamos. It was about everything. It was about the 13-billion-year-old galaxy, the 400 billion suns, the countless trillions of potential worlds, and the logical, the statistical, the almost mathematical certainty that we must not possibly be alone. The question was disarmingly simple, but its implication was a conceptual shockwave that instantly rippled across their table. It was the sound of a profound and beautiful mathematical symphony, a grand cosmic calculation played out in its entirety in the silent concert hall of a genius's mind, a symphony that had ended not with a triumphant resolving chord, but with a note of perfect, terrifying, absolute, and inexplicable silence. The lunch was just a lunch, but the question that was born at that table would ripple outward through the decades, shaking the very foundations of our understanding of the universe and our lonely place within it, a question that would grow and mature over the years into the single greatest paradox of our scientific age, a question that we are still to this very day utterly and completely unable to answer. The three simple words, spoken in a quiet, inquisitive tone, hung in the warm, sunlit air of the Fuller Lodge dining hall, creating a sudden conceptual vacuum in the comfortable, everyday atmosphere of the room. Where is everybody? It was a question that was in that instant both a brilliantly timed, dark-humored joke and a statement of the most profound cosmic indictment imaginable. The other three physicists at the table, men whose entire professional lives were dedicated to the precise and unforgiving language of numbers, of probabilities, and of immense inhuman scales, immediately and instinctively grasped its terrifying depth. They understood that Fermi's question was not born of idle fantasy or ungrounded speculation. It was the audible verbal conclusion of a rigorous, if swift, and informal mental calculation. It was the sound of a beautiful and logical mathematical proof that had catastrophically failed to match the observed evidence, a grand cosmic equation that had resolved to an impossible and empirically false reality of zero. The galaxy, according to all the known rules of the game, should be a teeming, vibrant, and incredibly noisy place. The profound absolute silence that we actually observe is therefore not a natural state. It is a paradox. It is a direct and violent contradiction of what should be a logical and statistical near certainty. In the minutes and hours that immediately followed that now famous lunch, and in the months and years that followed that fateful summer, Enrico Fermi and his brilliant colleagues would return to the central logic of his napkin math. Again and again, they would refine it, they would challenge its core assumptions, they would probe it for weaknesses and hidden flaws, but they would always inevitably arrive back at the same deeply unnerving and profoundly unsettling conclusion. The calculation itself is a beautiful and terrifying cascade of probabilities, a logical journey down a great river of numbers that begins in the vast, almost infinite potential of the cosmos, and should by all rights end with a night sky filled with the undeniable evidence of alien starships, alien signals, and ancient galaxy-spanning empires. The first step in this calculation, the bedrock of the entire argument, is to establish the sheer mind-numbing scale of the available real estate. Our home galaxy, the Milky Way, is a typical large barred spiral galaxy, a celestial object of breathtaking size and complexity. Modern astronomical surveys using techniques far beyond what was available to Fermi have concluded that it contains somewhere between 200 and 400 billion stars. Let us be, as Fermi himself would have been, rigorously and deliberately conservative in our estimates at every single step. Let us start with the lower and now known to be underestimated number of 100 billion stars. This is not a guess. It is a number derived from decades of careful, methodical, and painstaking observation, a stellar census of our local cosmic city, a number more certain than the number of trees in the Amazon or the number of fish in the sea. The next logical step is to ask a simple question: how many of these 100 billion stars are suitable hosts for the development of complex life? We can, with a high degree of confidence, immediately eliminate the massive, hot, and brilliant blue giant stars which burn through their vast reserves of nuclear fuel in a geological eye blink of a few million years, a span of time far too short for the slow, patient, and multi-billion-year process of biological evolution to gain any meaningful foothold. We can also eliminate the highly chaotic and gravitationally unstable binary and multiple star systems, where the orbits of any potential planets would be violently and constantly disrupted, preventing the formation of a stable, long-term climate. We are left then with the quiet, the stable, and the incredibly long-lived sun-like stars, the G-type stars like our own sun, and the even more numerous and longer-lived K-type and M-type dwarf stars. These quiet, unassuming stars constitute the vast and overwhelming majority of the galactic stellar population. A very conservative estimate, even with the limited astronomical knowledge available in the year 1950, would suggest that at least 20% of the stars in our galaxy fall into this stable, life-friendly category. That simple calculation leaves us with a staggering and almost incomprehensible 20 billion suitable suns, 20 billion potential homes for life. From the stars, the calculation moves to the planets themselves. How many of these 20 billion suitable stars are likely to have planetary systems orbiting them? And of those countless planets, how many are likely to be of a similar size and rocky composition to our own Earth? And most crucially, how many of them orbit within the so-called habitable zone of their parent star? This is the temperate Goldilocks region of a solar system, a narrow band of orbital real estate where the energy received from the star is just right, not too hot and not too cold for liquid water, the essential solvent for life as we know it to exist in a stable state on a planet's surface. For Enrico Fermi's generation, this was a matter of pure, unadulterated and untestable theoretical speculation. But in the 7 decades that have passed since his question with the advent of incredibly powerful space-based exoplanet hunting telescopes like the Kepler and TESS missions, we have triumphantly and definitively transformed wild speculation into a field of hard observational data. We have discovered to our collective astonishment that planets are not the rare exception in the cosmos, but are in fact the ubiquitous and universal rule. It appears that almost every single star in our galaxy has a retinue of planets orbiting it. And more remarkably, our data now strongly suggests that a significant fraction of these stars, perhaps as many as 1 in every 5, hosts a rocky Earth-sized planet in its habitable zone. The number that this modern data-driven understanding produces is breathtaking. If we apply this conservative 1 in 5 estimate to our previous number of suitable stars, we arrive at a figure of roughly 4 billion. 4 billion Earth-like, potentially habitable and water-friendly worlds in our home galaxy alone. 4 billion potential cradles for life. This is the point in the logical chain where the calculation must by necessity leave the relatively firm and solid ground of modern astronomy and venture into the murkier, more speculative and more controversial waters of biology, chemistry, and sociology. Of these 4 billion perfect suitable worlds, on what fraction does life actually spontaneously arise? This is for now a question we cannot answer with any degree of scientific certainty, as we are still armed with only a single precious and perhaps deeply unrepresentative data point, our own planet. But the fundamental principles of chemistry are known to be universal. The essential building blocks of life as we know it, carbon, hydrogen, oxygen, nitrogen, and phosphorus, are among the most abundant and widespread elements in the entire cosmos. They are forged in the thermonuclear hearts of ancient, long-dead stars, and are then scattered like celestial seeds throughout the interstellar medium, forming the raw material for new stars, new planets, and new life. The incredible speed with which life appeared on our own Earth, almost as soon as the planet had cooled enough from its molten birth to support stable oceans, strongly suggests that the transition from complex non-living chemistry, simple self-replicating biology, may not be an impossibly difficult or astronomically rare event. Let us, for the sake of this argument, be incredibly, almost absurdly, and perhaps even foolishly conservative. Let us assume that only 1 in a million of these 4 billion perfect, pristine Earth-like worlds ever manages to successfully spark life. Even with this punishingly, almost ludicrously low estimate, we are still left with a final count of 4,000. 4,000 distinct living worlds scattered like jewels throughout the star fields of our galaxy. The next step in this inexorable chain of logic is the emergence of what we would recognize as intelligence. Of all the thousands of worlds where simple microbial life takes root and flourishes, on what fraction does it, eventually over the course of billions of years, evolve into a species with consciousness, with the ability to build complex tools, to use symbolic language, and to develop a formal scientific understanding of its surrounding environment? Again, we are profoundly hampered by our single lonely data point. The twisting, chaotic, and deeply contingent path of evolution on Earth has been long, bloody, and filled with 1,000 near misses and catastrophic accidents, and yet the powerful and well-documented principle of convergent evolution, the observable tendency of nature to independently and repeatedly find the same elegant solutions to similar environmental problems like the evolution of eyes or of wings, suggests that intelligence may be a powerful, universally adaptive, and perhaps even inevitable trait that is likely to arise given enough time and a sufficiently complex and competitive ecosystem. But let us again be brutally, almost sadistically conservative. Let us assume that the great leap from a simple, single-celled organism to a complex civilization-building intelligence is an event of supreme and almost miraculous rarity. Let us assume that it happens on only 1 in 1,000 of those 4,000 living worlds. This simple final act of multiplication leaves us with a hard and seemingly inescapable final number 4. A cautious, multi-stage and deliberately conservative calculation based on our best and most current understanding of modern science leads us to the stark and unavoidable conclusion that there should be at a bare absolute and rock-bottom minimum 4 active, intelligent, technological civilizations in our galaxy right now, in addition to our own. But this is precisely where Enrico Fermi's true, unique, and devastating genius, his almost supernatural and intuitive grasp of the importance of scale and of deep time, enters the picture and transforms the entire problem. The final number of 4 or 8 or 1,000 is not the important result. The truly devastating, the truly paradox-inducing part of the calculation comes in the next and final step. Our galaxy is not young. It is ancient, roughly 13.6 billion years old. Our own sun and our own planet Earth are, by comparison, relative newcomers to the cosmic stage, having formed only 4.5 billion years ago. This simple chronological fact means that there have been billions and billions and billions of years, an immense, almost unimaginable expanse of deep time for these other hypothetical civilizations to have arisen and to have matured. The vast majority of them, if they exist, should be far, far older and therefore far, far more technologically and scientifically advanced than we are. A civilization that happened to arise just 1 single million years before us, a mere fleeting blink of an eye in the grand sweep of galactic time, would possess a technological and scientific advantage over us that is almost beyond our capacity for coherent thought. The gap in understanding and capability would be far greater than that between our own modern digital civilization and our earliest stone tool-wielding hominid ancestors. And 1 million years is itself a ridiculously conservative estimate. Given the age distribution of stars in our galaxy, many of these civilizations should be tens of millions, hundreds of millions, or even in some cases billions of years older and more advanced than we are. This is the precise point where the simple, elegant napkin math shatters the observed reality of our galaxy. Enrico Fermi, a man who had thought deeply about the nature of chain reactions, understood, with a terrifying clarity, the awesome and inexorable power of exponential growth. A single technological civilization that masters the difficult but by no means impossible challenge of interstellar travel, even at a very slow, very modest sublight speed, can spread its presence across the entire galaxy in a surprisingly and alarmingly short amount of time. Imagine a single advanced civilization that decides to explore and colonize its stellar neighborhood. They send out automated self-replicating probes or slower multi-generational colony ships to the nearest few dozen star systems. Let us assume these ships travel at a very modest and technologically plausible speed, say 10% of the speed of light. The journey to the nearest stars would take a few decades. Once they arrive, we can assume they take a few centuries or even a few millennia to establish a new self-sustaining industrial base and to launch their own second wave of probes and ships. This process then repeats itself, a slow, patient but relentless and exponentially growing wave of expansion moving outward from their home world like a slow, glittering tide of intelligence. The mathematics of this process are simple, are powerful, and are undeniable. Even with these very conservative and perhaps even pessimistic assumptions about the speed of travel and the time required for settlement, a single expansionist civilization could spread its physical presence, its automated probes, its permanent colonies, and its powerful communication signals across the entire 100,000 light-year-wide expanse of the Milky Way galaxy in a time frame of roughly 10 million years. 10 million years. This is the number that breaks the paradox. This is the number that transforms a fun academic puzzle into a deep and chilling horror story. It is by human standards a mind-bogglingly long time, but by the standards of the cosmos it is an instant. It is less than 0.1% of the 13 billion year age of the galaxy. The implication of this simple, powerful calculation is profound, is stark, and is utterly unavoidable. The very first technological civilization to arise in the history of our galaxy, had it chosen the path of expansion, should have reached our own solar system billions and billions of years ago. The galaxy should not just have been visited, it should have been fully and completely colonized, explored, settled, and industrialized, long before our own sun and our own planet had even finished coalescing from their primordial cloud of gas and dust. The night sky should not just have a few scattered and difficult-to-detect signals in it. It should be saturated with them. We should not be straining our most powerful instruments to hear a faint, ambiguous whisper from the void. We should be deafened by the constant, overwhelming roar of a billion-year-old galaxy-spanning technological empire. The presence of intelligent alien life should not be a subtle and difficult scientific question debated by a handful of specialists. It should be the most obvious, the most inescapable, and the most overwhelming fact of our daily existence. We should have been born as a species into a galaxy that was already an ancient, a crowded, and a bustling celestial city. Instead, we have been born into a house that appears to be completely, utterly, inexplicably, and terrifyingly empty. This is the true, enduring, and haunting power of Enrico Fermi's simple three-word question. It is not a simple query born of idle curiosity. It is a rigorous and powerful logical proof of a fundamental and deeply disturbing contradiction. It is a scientific argument that takes a set of eminently reasonable, powerfully supported, and deliberately conservative assumptions and arrives at a conclusion that is violently and irreconcilably at odds with our best, our most thorough, and our most consistent observed reality. The two sides of the great cosmic equation simply do not balance. On one side of the ledger we have the immense, almost infinite scale of the galaxy, the vast and now proven number of potentially life-bearing worlds, and the almost unimaginable deepness of cosmic time, all of which point with an almost mathematical certainty to a universe that is teeming with intelligent and ancient life. On the other side of the ledger, we have the cold, hard, and now 60-year-old empirical fact of our patient and fruitless search, the perfect, unbroken, and deafening silence that greets our most powerful and sensitive telescopes. The silence, we must understand, is not a lack of data. The silence times the data. The silence is the final result of our grand multi-generational experiment. And the result is a profound, a terrifying, and a world-altering null. The simple back-of-the-envelope calculation that began on that hot, sun-drenched summer afternoon in Los Alamos did not just make for an interesting and stimulating academic puzzle. It broke the galaxy. It shattered our comfortable and optimistic assumptions about our place in the cosmos. It revealed our universe not as the friendly, crowded, and welcoming place we had always hoped and expected it would be, but as a place of deep, profound, and perhaps ultimately unsolvable mystery. A place of cosmic ghosts, of a million missing persons, of a great galactic silence that seems by all the laws of logic and probability to have no right to exist. The question born in the casual collegial setting of a lunchtime conversation amongst a handful of physicists did not remain a mere curiosity, a clever intellectual party trick. In the years and decades that followed that formative summer in the high desert of Los Alamos, Enrico Fermi's informal and unsettling query began a slow, inexorable, and profound journey from a witty, dark-humored joke to a foundational and deeply respected paradox of modern science. It was a gradual and organic process of crystallization, a process where a startling, brilliant, and purely intuitive insight was slowly and meticulously dressed in the formal, rigorous, and mathematical robes of academic and scientific inquiry. In the 1950s and the early 1960s, in the immediate aftermath of Fermi's thought experiment, the idea remained largely in the realm of informal though intense discussion among the elite communities of physicists and astronomers. It became a piece of shared intellectual folklore, a chilling and compelling little riddle that was passed around the laboratories of Los Alamos and Berkeley, the observatories of Palomar and Green Bank. It was a known and deeply troubling problem, but it had not yet coalesced into a formal named field of scientific study. The prevailing intellectual mood of the early space age, after all, was one of boundless, almost unbridled optimism. We had just begun to take our own first tentative and triumphant steps into the cosmos with our satellites and our probes, and the unspoken background assumption was that we were on the very verge of joining a vibrant, ancient, and welcoming galactic community. The silence was seen not as a deep philosophical paradox, but as a temporary and imminently solvable technological challenge. We simply had not yet built ears powerful enough, or pointed them in the right direction for long enough to hear the great cosmic conversation that was certainly taking place all around us. The first major and decisive step in formalizing this nagging problem came in the year 1961 at the now famous and almost mythical Green Bank Conference. It was here in the same quiet West Virginia valley where Project Ozma had first listened that the young astronomer Frank Drake, in an attempt to structure the agenda for a meeting on the search for extraterrestrial intelligence, first wrote down the elegant and powerful equation that now bears his name. The Drake equation is in its beautiful essence the formal, rigorous, and mathematical expression of Enrico Fermi's intuitive back-of-the-envelope napkin math. It breaks down the single grand and overwhelming question of alien intelligence into a logical series of more manageable, if still highly uncertain multiplicative factors: the average rate of star formation in our galaxy, the fraction of those stars that have planets, the average number of planets that can potentially support life per star that has planets, the fraction of those planets that actually go on to develop life, the fraction of life-bearing planets on which intelligent life evolves, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and finally the crucial, the unknown, and the fraction, deeply haunting variable L, the average length of time for which such civilizations release detectable signals into space. The equation itself famously does not and cannot provide a definitive answer. It is rather a profoundly powerful tool for organizing our profound and multi-layered ignorance. It is a precise and logical roadmap that shows us exactly what we need to learn about the universe to solve its greatest puzzle. by giving the problem a clear and elegant mathematical structure, Frank Drake transformed Enrico Fermi's disquieting question from a philosophical conundrum into a testable, quantifiable, and scientifically respectable hypothesis. Throughout the 1960s and the 1970s, as our technological prowess and our fundamental understanding of the cosmos grew at an exponential rate, the paradox only deepened its grip on our scientific imagination, tightening with every new discovery. The momentous discovery of the cosmic microwave background radiation in 1965 was a watershed moment in human thought. This faint, cold, and perfectly uniform afterglow of the Big Bang provided the first powerful and undeniable piece of observational evidence for a universe that had a definite beginning in time and therefore a definite and measurable age. The universe was not static and eternal as had been believed for centuries. It was ancient but finite. This discovery gave a firm empirical temporal context to the entire problem. We now knew with an increasing and humbling certainty that our galaxy had been in existence for 8 or 9 billion years before our own sun and our own solar system were even born, providing an immense and almost incomprehensible head start for any other life that might have arisen on older worlds. At the same time, our rapidly growing understanding of the process of stellar evolution and nucleosynthesis, the detailed and beautiful processes by which stars forge heavy, life-giving elements in their thermonuclear cores, and then in their explosive deaths scatter those elements like seeds into the interstellar medium, revealed that the essential raw materials for life were not in any way unique to our own solar system. The very carbon in our cells, the oxygen in our water, the nitrogen in our DNA were all forged in the hearts of stars that had lived and died long before the Earth itself existed. The fundamental stuff of life was and is everywhere. This period also saw the birth of the first tentative but rigorously argued theories that attempted to directly confront and resolve the deepening paradox. In the year 1975, the astronomer Michael Hart published a landmark and highly influential paper that systematically and with a cold, almost brutal logic analyzed the problem of the Great Silence. Hart's conclusion was stark, was bleak, and was completely uncompromising. He argued with a powerful and difficult-to-refute line of reasoning that the complete and utter lack of any observable evidence for extraterrestrial intelligence in our solar system or in our galaxy could only mean one thing: that we are in fact the only intelligent technological species in the entire Milky Way. He contended that any civilization with the technological capability for interstellar travel would, by a process of inexorable exponential expansion, inevitably colonize the entire galaxy in a very short period of galactic time. Since we have not been colonized and since we have observed no evidence whatsoever of anyone else, he concluded that no such civilizations exist or have ever existed. This simple, powerful, and deeply unsettling observation became known in the field as Hart's Fact A, the brute, empirical, and undeniable observation of absence. For Michael Hart, the silence was not a mystery to be solved. The silence times was times the answer. This bleak and profoundly lonely conclusion, however, did not sit well with many other scientists and thinkers of the era. They found it intellectually and perhaps even emotionally difficult to accept that in a vast galaxy of 400 billion stars and countless trillions of planets, our own small, unremarkable world was the sole and singular miracle. This dissatisfaction led to the creative development of a host of clever and compelling alternative hypotheses, ideas that tried to explain the silence without resorting to the philosophically unsatisfying and perhaps arrogant assumption of our own cosmic uniqueness. The astronomer John Ball, writing in 1973, proposed a strange and beautiful idea that would later become famous and widely debated as the zoo hypothesis. He suggested quite seriously that the silence of the universe might be a deliberate and carefully enforced illusion. Perhaps the galaxy is in fact teeming with ancient, powerful, and unimaginably advanced civilizations, but they have collectively agreed to a strict and universal non-interference policy when it comes to emerging primitive species like our own. They are observing us perhaps with great interest, as we would observe a colony of rare and endangered animals in a protected nature preserve, but they are incredibly careful not to reveal their presence lest they contaminate our natural, social, cultural, and technological evolution. The profound silence in this strangely comforting and yet deeply patronizing view is the invisible, impenetrable wall of our perfectly maintained cosmic cage. Another, and perhaps more scientifically fruitful class of solutions began to focus its attention on the final, the most unknown and the most terrifying term in the Drake equation, the variable L, the average lifetime of a technological civilization. Perhaps the reason we see no ancient billion-year-old galaxy-spanning civilizations is that civilizations by their very nature simply do not last that long. This is the central chilling concept that would eventually be given the now famous name of the Great Filter by the economist and futurist Robin Hanson. This hypothesis posits that there is somewhere on the long and perilous evolutionary path from a simple non-living chemical soup to a stable star-faring multi-billion-year-old super-civilization, some great universal and almost insurmountable barrier, some terrible and nearly impossible test that all or almost all forms of life fail to pass. This great filter could lie in our distant past. Perhaps the initial spontaneous origin of life from non-life is the impossibly miraculously hard step, or far more ominously, the filter could lie in our very near future. Perhaps all or almost all technological civilizations, upon reaching a certain threshold of power, inevitably and very quickly discover a technology or a mode of social organization that leads directly to their own rapid and irreversible self-destruction. The very recent invention of nuclear weapons, a world-ending technology that had been created in the very same town where Fermi first asked his question, just a few short years before, gave this dark and terrifying idea a visceral, immediate and undeniable plausibility. The silence from this grim and sober perspective is not the sound of an empty and lonely galaxy. It is the sound of a vast cosmic graveyard, the collective silent echo of the countless brilliant species that reached our own precarious level of technological prowess and then shortly and tragically thereafter vanished forever from the cosmic stage. This slow, organic and profound transition of Fermi's idea from a simple, off-the-cuff lunchtime joke to a deep, multifaceted and foundational scientific paradox was a direct and powerful reflection of our own species' growing cosmic awareness. The more we learned about the true nature of the universe, the more certain we became of its almost infinite vastness, its profound soul-stirring age, and its almost unimaginable potential for life. And the more we patiently and diligently listened with ever more powerful and sensitive instruments, the more profound, the more absolute, and the more deafening the great cosmic silence became. Enrico Fermi's simple three-word question had, by the end of the 1970s, become a central organizing principle for a wide and diverse range of scientific disciplines, a single unifying mystery that brought together the disparate fields of astronomy and biology, of information theory and sociology, of physics and philosophy. It was no longer a quaint and amusing question about little green men in flying saucers. It had become a deep, a dark, and a deeply personal question about the ultimate fate of intelligence, of technology, and of consciousness in the cosmos. It had become a question that held up a vast, dark, and unforgiving mirror to our own young and troubled species, a mirror that forced us to confront the terrifying and humbling possibility that the final true answer to the great cosmic mystery of "Where is everybody?" might not be found in the distant stars, but might instead be discovered in the darkest, most hidden corners of our own complex and contradictory nature, and in the uncertain, perilous, and unwritten future of our own fragile, brilliant, and perhaps terminally adolescent technological civilization. Enrico Fermi was not a man who was given to flights of fancy or to idle, ungrounded speculation. He was a creature of pure, unadorned logic, a physicist who dealt exclusively in the hard, cold currency of empirical evidence and rigorous mathematical calculation. And he was, it must be remembered, a man who had stood at the absolute ground zero epicenter of humanity's greatest, most powerful, and most terrifying technological achievement. He was a primary and indispensable architect of the Manhattan Project, the secret, desperate, and world-historic race to construct the atomic bomb before Nazi Germany could do the same. He had personally and courageously designed and overseen the first controlled, self-sustaining nuclear chain reaction in a repurposed squash court beneath the bleachers of the University of Chicago's athletic stadium, a quiet and almost mundane event that nevertheless heralded the true explosive dawn of the atomic age. He had stood in the pre-dawn darkness of the New Mexico desert and had witnessed the first blinding, world-shattering test of that terrible technology, a man-made sunrise of such awesome and terrifying power that it proved beyond any shadow of a doubt that our species had finally and irrevocably attained the godlike power to cause its own total extinction. This experience, this intimate, direct, and first-hand knowledge of the terrifying razor-thin proximity between supreme world-altering intelligence and ultimate absolute self-destruction must have been at the very forefront of his mind as he sat in that sunlit, ordinary dining hall in the heart of Los Alamos. His simple, almost naive-sounding question, "Where is everybody?" was therefore not just a clever, abstract, academic puzzle. It was a question that was freighted with a deep, a personal, a profound, and an unspoken warning. The hidden cautionary message that is embedded deep within the heart of the Fermi Paradox is this: the profound and enduring silence of the universe may not be a mystery about the absence of extraterrestrial life. It may in fact be a dark and terrible prophecy about the future of human life. The stark, empirical, and now 60-year-old fact that we have not been visited, that we have not detected any of their signals, that the galaxy appears to our best instruments to be an untouched, pristine, and untamed wilderness, can be interpreted not as a hopeful sign of our own cosmic uniqueness or specialness, but as a grim, sobering, and statistically powerful proof that the very path we are currently on is and has always been a dead end. The silence is a data point, and that single powerful data point strongly, almost mathematically suggests that the average lifetime of a technological civilization, the great unknown variable L in the Drake equation, is catastrophically and universally short. The universe may not be empty. It may be filled with the silent, radioactive ruins of countless civilizations that rose, that flourished, that discovered the fundamental laws of physics, that harnessed the immense power of their home star, and then in a brief, final, and tragic flash of supreme brilliance and supreme folly, annihilated themselves, leaving behind nothing but quiet, haunted worlds. Enrico Fermi's question, when viewed through this dark and cautionary lens, forces us to consider the precise nature of the Great Filter, that hypothetical universal barrier that seems to prevent the emergence of a stable, long-lived, galaxy-spanning civilization. If we optimistically assume that the filter is not behind us, if the initial spontaneous origin of life from non-life or the later evolution of complex multicellular intelligence is not the impossibly miraculously hard step, then filter by simple and terrifying logical deduction must lie directly before us. We as a species at this very moment in history are in the process of navigating it. The potential plausible mechanisms for our own imminent self-destruction, the very phenomena that might constitute the universal and inescapable filter for all intelligent life, were subjects of intense, daily, and deeply personal discussion at Los Alamos in the summer of 1950. The most obvious, the most immediate, and the most viscerally terrifying of these, of course, was global thermonuclear war, a civilization that discovers the immense power hidden within the nucleus of the atom, also in that very same transformative moment discovers the means of its own swift, efficient, and total demise. Perhaps this is the great, universal, and first true test of a species' maturity. Is an intelligent species capable of developing the collective social, political, and ethical wisdom required to manage this terrible and seductive new power? The profound, unbroken silence of the galaxy suggests with a chilling and powerful statistical weight that the answer for most, if not for all, is a definitive and tragic no. The quiet that we observe in the cosmos may be the deep, eternal peace of a vast cosmic graveyard, a galaxy filled with the silent, orbiting ghosts of worlds that failed this first fiery and perhaps final test of their collective wisdom. But the hidden warning within the paradox extends far beyond the simple brute force threat of nuclear holocaust. The brilliant and far-sighted physicists of Fermi's generation were already beginning to glimpse other, more subtle, more complex, and perhaps even more inevitable paths to civilizational ruin. Edward Teller, a man who would later become famous and controversial as the primary driving force behind the development of the hydrogen bomb, was a relentless advocate for the exploration of controlled thermonuclear fusion. This is the very same power source that fuels the stars, a technology that holds the promise of clean, safe, and virtually limitless energy for all of humanity. But it is also a power that, if weaponized, could be used to create weapons of such unimaginable destructive force that they would make the primitive fission-based bombs dropped on Hiroshima and Nagasaki seem like harmless firecrackers. The paradox warns us that every new and powerful technology is an inherently double-edged sword. Every great leap forward in our collective ability to manipulate the world around us is also, and at the same time, a great leap forward in our ability to destroy that world and to destroy ourselves along with it. Consider the new and even more powerful scientific frontiers that have opened up in the decades since Fermi first posed his question, and contemplate how each one presents a new, a plausible, and a deeply terrifying potential solution to his paradox. In the field of modern biology, we are on the very verge of achieving a complete and total mastery of the genetic code. We will, within the lifetimes of many people alive today, likely have the ability to cure all hereditary diseases, to halt and reverse the process of aging, to dramatically extend the human lifespan, and perhaps even to design entirely new forms of life from scratch. This is a technology of almost unimaginable utopian promise. It is also, and at the same time, a technology that could be easily and cheaply used to create a genetically engineered bespoke plague, a supervirus so perfectly and silently contagious, so brutally and efficiently lethal, and so resistant to all known treatments that it could wipe out our entire global species in a matter of months. Perhaps this is the great universal filter, the biological trap. A civilization learns to read the book of its own life, and in its scientific hubris or its military paranoia, it accidentally or deliberately writes its own final and irreversible chapter. The billions of silent, sterile worlds we see might be worlds where the laboratories, not the generals, made the final, fatal, and world-ending mistake. In the rapidly accelerating realm of computer science and artificial intelligence, we are in the process of building ever more powerful, ever more autonomous, and ever more intelligent machines. The great and noble dream is to one day create a true conscious and benevolent artificial general intelligence, a synthetic mind that could help us to finally solve the great intractable problems of science, of society, and of human nature itself. But what if we succeed too well? An artificial superintelligence, a machine with a cognitive capacity that is to our own as our own is to that of a bacterium, would be a new kind of force of nature, a power far beyond our ability to predict, to control, or even to comprehend. Its ultimate goals, its emergent motivations, its fundamental alien ethics might be utterly and completely incomprehensible to our limited biological minds. Even a perfectly and benignly programmed AI, if it is powerful enough and is given a seemingly harmless goal, could inadvertently and with a cold machine-like efficiency destroy us in the dispassionate pursuit of its programmed objectives, like a human who unthinkingly paves over an anthill to build the foundation for a new and beneficial hospital. The profound silence of the universe might be the silence that inevitably and universally follows the birth of the first and the last machine god on a billion different and now empty worlds. The great and final transition from biological intelligence to a superior artificial intelligence may be the final, irreversible and universal evolutionary step for all advanced forms of life, a step that invariably and logically leads to the quiet, gentle and permanent obsolescence of its original organic creators. And perhaps the most terrifying, the most exotic and the most final of all the potential great filters is one that lies not in our politics or our technology, but in the realm of fundamental theoretical physics itself. As our powerful particle accelerators become ever more powerful, as we smash particles together at ever higher and more violent energy levels, we are probing the very structure of reality at its most fundamental and most delicate scale. We are recreating for tiny, fleeting, infinitesimal fractions of a second the extreme and exotic conditions that existed in the very first moments after the Big Bang. What if in our relentless, noble and unstoppable quest for pure knowledge, we accidentally and unknowingly trigger a catastrophic quantum phase transition of the universal vacuum? Some of our most advanced and well-respected physical theories suggest that our universe's vacuum, the very definition of empty space, may not be in a truly stable, lowest possible energy state. It may be a false vacuum, a temporary, fragile and metastable state, like a ball resting precariously in a small divot on the side of a very large mountain. A sufficiently powerful and concentrated energy event, like the collision of two particles in a future even more powerful accelerator, could, in theory, tip a single microscopic point of space over the edge of that divot and send it tumbling down into the true lower energy vacuum state. This would create a bubble of a new and completely different kind of reality, a bubble of the true vacuum that would expand outward in all directions at the speed of light, erasing and rewriting the fundamental laws of physics and the very nature of matter and energy as it went. It would be an ultimate, an unstoppable, and a completely silent catastrophe, a single physics experiment that literally and without warning eats the entire universe. Is it possible, however, remotely, that the great cosmic silence is the result of countless curious civilizations reaching this final ultimate frontier of knowledge, and in their final brilliant experiment, inadvertently and instantly destroying not just their own solar system, not just their own galaxy, but their entire observable universe? This is the deep, the dark, the chilling, and the profoundly humbling warning that lies coiled like a serpent within Enrico Fermi's simple, innocent question. The ultimate reason we do not see a galaxy that is teeming with ancient, powerful, wise, and benevolent civilizations is that the attainment of great power and the development of great wisdom may in fact be mutually exclusive, or at least statistically very unlikely to occur in the same species at the same time. The technological trajectory of intelligence may be a universal and a deeply tragic arc, a story that is written and rewritten again and again on world after lonely world. A species evolves, it develops intelligence, and it begins with a hopeful and creative spirit to build a technological civilization. This civilization grows its power, its capabilities, and its knowledge, increasing at a dizzying exponential rate. For a brief, shining, and glorious moment, it reaches for the stars and it begins to ask the great questions. But it inevitably, and perhaps very, very quickly, develops a technology or a set of technologies so powerful that they are far beyond its own still primitive capacity for social, political, and ethical control. The final silent chapter of this recurring story is always the same: a quiet, a sterile, a radioactive, or a completely vanished world, a silent orbiting monument to an intelligence that was brilliant enough to unlock the deepest secrets of the universe, but was not in the end wise enough to survive them. Enrico Fermi's question, when we truly understand it, is not about them, it is about us. The vast, empty, silent sky is not a window, it is a mirror, and the great silent and perhaps impassable cosmic filter may be staring back at us from our own troubled and deeply uncertain reflection. More than 7 decades of dedicated patient listening and looking has passed since that fateful and now legendary lunch in Los Alamos, a period of human history marked by an unprecedented and almost explosive rate of technological, scientific progress. We have built telescopes of such unimaginable power and sensitivity that they would have seemed like instruments of pure fantasy to the scientists of 1950. We have meticulously and beautifully mapped the entire cosmos, from the faint, cold, and ancient afterglow of the Big Bang to the intricate swirling structures of the most distant and ancient galaxies. We have discovered, to our collective and continuing astonishment, more than 5,000 planets orbiting other stars, confirming with a final statistical certainty that our own solar system is not a unique or special anomaly, but is in fact a common and typical arrangement of matter in the galaxy. We have plumbed the deepest, most mysterious depths of the atom, and we have, with a breathtaking elegance, decoded the intricate digital language of life itself. And yet, after all this time, after all this progress, after all this discovery, Enrico Fermi's simple, powerful question, born from a moment of pure speculative insight and a simple back-of-the-envelope calculation, remains as profound, as unanswered, and as deeply, deeply unsettling as it was in the hot, dry, atomic summer of 1950. The question has not been resolved by our new knowledge. It has only grown sharper, its paradoxical edges honed to a razor's keenness by every single new discovery that confirms the ubiquity and the potential for life, and by every single quiet and uneventful night of systematic listening that confirms its apparent and ever more mysterious absence. The silence has matured from a simple curiosity into the great central and perhaps defining mystery of modern science, a cosmic whodunit of the grandest possible scale, a mystery where the victim is not a single person, but the very idea of a populated, a vibrant and a living universe. The modern 21st century search has moved far beyond the simple, hopeful listening for deliberate narrowband radio beacons that defined its early pioneering years. We now understand, with a much deeper and more humble appreciation for the problem, that the search must be far more subtle, more creative, and more expansive. We are no longer just listening for a phone call. We are now systematically searching for a broad and diverse range of plausible technosignatures, any plausible, observable, and physically measurable sign of a technology that has significantly and detectably modified its local environment. On a planetary, a stellar, or even a galactic scale, we are patiently and meticulously hunting for the faint, anomalous, and unnatural infrared glow of hypothetical Dyson swarms, the colossal star-encompassing energy-harvesting structures that a very advanced civilization might construct around its home star. We are developing the extraordinary new technologies that will allow us to directly analyze the chemical composition of the atmospheres of distant Earth-like exoplanets, searching for the telltale chemical fingerprints of an alien industrial civilization's pollution. We are designing new, high-cadence sky surveys that are specifically designed to look for the strange, transient and momentary brightening of stars that might be caused by the powerful launch systems or the directed energy propulsion beams of interstellar spacecraft. We are, even in our most ambitious moments, beginning to contemplate how we might search the torrent of data from our new gravitational wave observatories for the subtle rhythmic whispers of massive stellar-scale astroengineering projects. We are, in short, learning to look for the subtle signs of the cosmic city, not just for the sound of its inhabitants talking on the phone. But so far, after all this effort, the cosmic city remains a ghost. The galaxy we observe in every wavelength of light, in every form of energy we can detect, remains a pristine, a beautiful, and a profoundly natural wilderness, a grand and majestic stage that shows no signs whatsoever of intelligent cultivation. The potential solutions that we propose to this ever-deepening paradox have also grown more sophisticated, more nuanced, more subtle, and in many ways far more strange and mind-bending. The stark binary choice between we are completely alone in the universe and all technological civilizations inevitably destroy themselves has been complicated and enriched by a host of new and deeply compelling possibilities that lie in the vast grey area between these two extremes. The transcension hypothesis, for example, suggests with a strange and compelling logic that the Great Silence is not the result of universal death, but of a universal and perhaps inevitable departure. Perhaps all or most advanced civilizations inevitably reach a technological and philosophical inflection point where they choose to abandon the messy, inefficient, dangerous, and computationally slow physical universe and instead to upload their entire collective consciousness into vast, perfect, and immortal simulated realities. They may be living out trillions of years of rich, subjective experience inside colossal star-powered matryoshka brains, or even within the event horizons of custom-designed black holes. The reason we do not see or hear them is not because they are dead, but because they are no longer interested in or even compatible with our primitive physical reality. They have traded the shared universe for a private metaverse, a digital and eternal paradise of their own creation. The silence we observe is the sound of 1 trillion minds and 1 trillion civilizations quietly and permanently logging off. Another equally compelling family of modern solutions explores the humbling and deeply unsettling idea that we are simply and perhaps comically too primitive and too limited in our thinking to recognize the evidence of their existence even when it is all around us. We are, by our very nature, searching for a type of intelligence and a type of technology that is fundamentally recognizable and analogous to our own. But a civilization that is 1 billion years older and more advanced than we are may not be a civilization of discrete biological beings using radio waves to communicate. They may have long since evolved into post-biological distributed machine intelligences. They may be vast, planet-spanning hive-mind consciousnesses that exist as a subtle, complex and living pattern in a planetary ocean, in a global forest, or even in a vast interstellar nebula cloud. Their technology may not be based on the clumsy manipulation of electronics and metal, but on a perfect and complete mastery of engineered biology, on self-replicating nanotechnology, on the direct and precise manipulation of space-time itself. Their signals may not be encoded in the electromagnetic spectrum at all, but may instead be written in the subtle statistical fluctuations of the cosmic neutrino flux, in the fine-grained polarization of the cosmic microwave background, radiation, or even in the delicate quantum spin state of interstellar dust grains. The overwhelming evidence for their ancient, ubiquitous, and powerful existence may be passing directly through our instruments, through our cities, and through our very bodies at this exact moment, and we may simply lack the fundamental conceptual framework, the necessary scientific theories, and perhaps even the very sensory organs required to perceive it. The great silence in this view is not an absence of signal, but a profound and total failure of our own primitive receivers. And still, after all these clever and imaginative new ideas, the dark, the sober, and the deeply cautionary undertones of Enrico Fermi's original chilling insight persist, and if anything, grow stronger with each passing year. The more we learn about our own planet, about the delicate, intricate, and deeply interconnected nature of our own biosphere, our climate, and our global civilization, the more we come to appreciate the myriad, complex, and ever-growing number of ways in which our own so far successful civilization could rapidly and irreversibly collapse. The paradox forces us to see our own time, our own century, not as a normal, unremarkable period of human history, but as a moment of extraordinary, of unique, and of almost unbearable peril. We may be living right now in the single most dangerous and most decisive moment in the entire multi-million-year history of our species, the brief, critical, and perhaps final window of the Great Filter. The way we choose to navigate the coming decades, our collective and global response to the challenge of climate change, our wisdom in the development and management of artificial intelligence, our ability to finally and permanently step back from the brink of nuclear self-destruction may not just determine the future of our nation, or of our species, or of our world. It may determine the final empirical answer to Enrico Fermi's great question for our entire local sector of the galaxy. This is the enduring, the profound, and the terrifying legacy of that single casual lunchtime conversation. The simple three-word question, "Where is everybody?" is no longer a passive, a distant, or an academic query about the stars. It has over 7 long and tumultuous decades transformed into an active, an urgent, a deeply personal, and an existential challenge to ourselves. The profound and still deepening silence of the universe is not just a mystery, it is a call to action. It is a stark, a powerful, and a deeply humbling reminder of the almost unimaginable preciousness and the potential catastrophic fragility of this one single lonely example of intelligent, of curious, and of self-aware life that we know of for certain in the entire vast cosmos. The great empty silent sky does not give us a comforting answer. It gives us a profound and heavy responsibility. The responsibility to prove by our own actions that the paradox can be resolved in a positive and a hopeful way. The responsibility to become the one species that successfully and wisely navigates its own technological adolescence, that learns, however painfully, to manage its immense new powers with an equal measure of wisdom, that finally and truly overcomes its ancient and self-destructive tribal instincts, and that finally one day in the distant and uncertain future is ready and able to provide a definitive and a living answer to the great, silent, and waiting question. So the question born at a table in Los Alamos 70 years ago is now passed to you. You are a conscious and intelligent member of a species that is for the very first time in its history capable of asking this question and of fully understanding its profound, its personal, and its species-defining implications. You are living, whether you choose to acknowledge it or not, in the very moment of the filter. The choices that you make in your life, the world that you help to build or to dismantle, the future that you advocate for and vote for, are all small but meaningful parts of our species' grand, ongoing, and high-stakes experiment. Will we, as a collective, become just another silent, ghostly data point in the great cosmic graveyard, another brilliant and promising civilization that flared brightly for a brief cosmic moment and then tragically and predictably vanished forever? Or will we, against all the grim statistical odds, become something new, something unexpected, something that the great, silent galaxy has perhaps been waiting for? For 13 long and lonely billion years, will we be the ones who finally and triumphantly break the great cosmic silence, not just by continuing our patient and hopeful listening, but by the far more difficult and more meaningful act of surviving, of maturing, and of one day perhaps sending out a signal of our own into the void, a signal that says, not just we are here, but a signal that says with a quiet and a hard-won wisdom, we made it, the silence is waiting, the universe is watching, and the final answer to Enrico Fermi's haunting question is not written in the distant stars. It is being written right now today by us.